Okay, hello, my name is Juozas, and today I'm going to speak about predicting company credit rating using artificial intelligence techniques from publicly available data. So maybe you would agree with me if I would say that for all human existence, the knowledge of our partner's behavior is crucial. If it's trustworthy, is it a long-term relationship or something like that? So same occurs to the companies. If company doing some business with other company, we want to evaluate the risk. If it's going to be, for example, long-term or it's risky, if we have to put some provisions, if it's going to bankrupt or something like that. So one of the techniques or metrics to show if the company is going to be risk or not is credit score or credit rating in other words. Also, it's I have to mention that European Union has announced that all the countries of Europe has to open their data. So we are going to use that data of Lithuanian companies, which is publicly available and free. Okay, so about data set, we're going to use financial features from Registered Center of Lithuanian and the credit score from Risk Planner risk management tool. So these are 7 main features of financial information and 1 additional credit rating. Credit rating differs from 1 to 5, while 1 being the highest and 5 the lowest, and also has 5 different classes of risk from A to E. In addition of these 7 metrics, 5 or I would say 6 ratios was calculated. Total assets is just long-term and short-term sum of assets, and 5 different scores which was able to calculate from the data, initial data of 7 features. I'm not going to talk about each of them, but some of the formulas is provided in the screen. The distribution of the data for each year is kind of similar, but we do not have too much data. For example, at the start it was about 8,400 records, but after preprocessing data, deleting null values, deleting noise and very high outliers, we reached about 6,000 records. This slide is kind of important. I will try to explain as detailed as I can. For the experiments, there will be 4 different scenarios of data sets. As I mentioned before, there was 7 initial features of financial data and 6 additional ones. So the data will be split to only 7 initial features and only 7 with additional 6. So it's 2 part of data set, and the different training and the testing would be applied for also splitting randomly for training 89 to match the data for other years than 2022, and for testing 11%. And for other parts, as I said, the training will be going to done with previous years and the testing with the newest one. And this example is 2022. So it's 4 different data set approaches. With each of them, the experiments will be conducted. What kind of methods were used? For machine learning techniques based on the literature analysis, we have chosen artificial neural network and random forest because it was one of the most popular and promising methods. Just for comparison reasons, we took few simple statistical methods. It's linear regression and Huber regression. Huber regression is a little bit better than linear regression if the task of outliers. and we proposed additional method which would be separated mainly into two parts. One, using artificial neural network to classify and try to predict the class of the record, and then based on the predicted class, choose the different INN model to try to predict numerical values. So yes, we had enough data for D and E classes, so we had to combine them. Evaluation metrics for prediction. So in the left part, you can see main 4 features of evaluation metrics for random forest, for artificial neural network, and linear and Hubble regressions. And for classification task, that only part of proposed method. We used 4 different evaluation metrics: is accuracy, precision, rapport, F1 score. So what kind of experiments we conducted? So for artificial neural network, we changed hyperparameters, batch size, epochs, atomizer, and activation function. And with each set, each set of hyperparameters, and for each data set I showed before, all the experiments were conducted, and maybe it was about 2000. For each data set, the best results which achieved best results is shown here in the table 3 with the hyperparameters which has achieved that best results for each data set of an model. Same goes to random forest, just different hyperparameters, n estimator, max depth, min samples of split and leaf. And same goes to table 5. For each approach of data set, these results achieve the best results, these parameters. And the results, data set, all, that means that taking all financial features, 7 initial ones, and 6 additional calculated. And we can see the results that 2002 means that we are predicting the newest year and training on the previous, and random is split randomly. We can see that taking all the features and predicting on the newest years shows the better results a little bit, but it shows the better results for all the models. Also, artificial neural network outperforms other techniques. Similar to last tables, fin data means that we are taking only initial ones, 7 features, financial features. And we can see that for table 8, when we're predicting the newest year of the data, we're getting also better results. But for the first time, random forest outperformed the artificial neural network in almost all metrics. We can see that best of the best, that scenario of artificial neural network first, the distribution of actual values and predicted values. We can see that it's kind of going okay, but we are not very happy because it differs on about 0.25 score, which kind of high, taking in mind that there differs from 1 to 5. So we are going to work on that to make maybe 0.15. Okay, the results of proposed method, but these results are very promising. As you see, the scores is very low. It means that very low errors, but the data had to be split into 4 classes. That means that we just didn't have any data to perform the split D and E classes. We had to combine them. This result is promising, but it needs to be done more with architecture and data. And in conclusions, so machine learning algorithms, as you saw, outperform statistical methods very far away. The best results were achieved using artificial neural network for taking all financial features, initial and calculated ones, and trying to predict 2022 year's data. Also, what is important to say that calculating additionally attributes features from the initial ones improves the results of the models. We saw from the tables that predicting and training randomly is lower performance than training from previous years and trying to predict the newest one. And proposed method is promising, but we need more data. So future work is focusing on getting more data, just not in Lithuanian companies, but in Europe also. Focusing more on the proposed method because it's promised better results than just to predicting from the data, but to firstly classification and do the prediction task later on. And yeah, no questions, thank you, but the second presentation.
So thank you for that. And now I suppose completely different field.
Yes. Maybe a little bit to the heart, this one. As you already know, hello, I'm Juozas, going to present the basketball board detection using YOLO algorithms. And introduction, maybe you can't tell now, but I like to play basketball 2 or 3 years ago. I like to training alone, but it kind of getting distraction to calculate the shots, trying to remember what I did in last week, how it performs, am I achieving something or not in the performance. So I decided to make a kind of program which would do instead of me to count the shots. The first task to do that is to find the basketball board, and it's possible basketball shooting box, rim, and the net. So we, in the next research, we could find the ball and try to predict the score. But for this research, we are going to focus on finding, detecting, and recognition of basketball board. The data set. So we filmed in one indoor court with 2 different mobile devices, approximately about placing them 45 plus minus 10% degree of the court in the red areas. Also, I have to mention that the camera has to be static. We're taking that in mind, that camera is static and it's filming whole shots. And for each of the, in total, there was about 170 videos with 3 shots with different accuracy, most of 0 or 1, but it doesn't matter. So taking each frame of the first frame of each video, we have about 200 images for training and trying to validate the results. For methods, we took the YOLO algorithm, which is more rapidly increasing and improves in accuracy and in detection rate. And we took for the experiments 3 different YOLO versions, version 5, 7, and during the research 2 or 3 months ago, the YOLO version 9 was published, not fully, not all the parts of it. We couldn't change the architecture, but we could perform the experiments of YOLO 9, so we did. The environment of our experiment is Google Colab, free version. It's match our needs. Also Python and other libraries which was needed for the experiments. For example, maybe GitHub repository of the model or some other libraries to represent the graphs or something like that. But this kind of environment. we are performing different experiments with different training image size, batch size, epochs, and for YOLO 5, we tried to change the depth and width of the model. By the way, I have to mention that for YOLO 7 or YOLO 9, we used pre-trained weights, but for YOLO 5, we used from scratch because we wanted to check the architecture by ourselves, how it performs. And evaluation metrics of our experiments is precision. Recall map 0.5 and map mean average precision 0.5 till 0.95 by the step being 0.05. In addition of these evaluation metrics, we calculated inference time of a detection task and the model size itself. So results of map mean average precision from 0.5 till 95. We can see in the picture why there is no other evaluation metrics like previous, why no precision recall and map 0.5. They all performed very similarly because we didn't want them to show because it just differs very, very low. For the map score of 0.5 and 95, we can see that YOLO version 9 outperforms other models in the kind of yellow stuff. And yes, I forgot to mention, we used two different YOLO versions of 9 C and E. And we can kind of make a conclusion that it's simple, but getting bigger training image size shows better results. And the results of YOLO 5 architecture, it's kind of messy, but I will try to explain. The same dots represents the same depth of the model. The color represents same width of the model. And the black one is just a simple, by default, 1x1 depth and width. So we can see that most of the time, if the model depth is 0.4, it performs better than 0.6, the depth of 0.6. The width of the model, it kind of performs less well, I guess. Yeah, it's a little bit difficult to say, but I hope you get the point. Also, we can say that at the top of 640 training image size, we have a higher score than the model was by default, 1x1. But we did not lose very much score in comparison with other models if we're changing the architecture. And about the size, also it's a little bit, Eurovision, the different colors, but we can see that tendency that increasing the model size also increase the score of map. Same is with inference time, it's detection in milliseconds. But what we can say too, that, for example, if we're taking in a YOLO 5, this is YOLO 5 being by default 1x1, and the results just differs by 0.03. 0.03, but the inference time almost doubles up. That means that it takes lower time twice as before. So it's kind of important part because we do not lose too much accuracy, but we are winning on the inference time. Same is a little bit with the model size. As we can see, the YOLO version 9 performed the best, but it also took very much, differs very much of the model size in comparison with other models. So in conclusion, YOLO version 9 outperforms other models and reach almost 0.9 map score of from 0.5 to 95. YOLO version 7 is the fastest. while depth and width are set to 1. The YOLO 5 could outperform in the speed of YOLO 7, but with different architecture, depth and width. Also, YOLO version 5 slightly outperforms YOLO 7 in almost all evaluation metrics. And of course, as mentioned, changing the architecture of YOLO 5 gives just few low cost of performance, but it's we win on getting less inference time and smaller model size. Why it's important? If you maybe we're going to use in some wild device the model, it has to perform very well and has to be in lower size. And of course, I have to mention that the higher training size, the higher score of the evaluation metrics. And future work would be to perform the analysis with the YOLO architecture deeply. For example, try to perform different activation functions, optimizers, must add additional data of different chords, maybe some filmed by myself too, but maybe from publicly available data. Also, the final product of this research would be to make the system which would count shots instead of me. And that's it. Thank you. And questions, you can write me down, or you can find me on Facebook.